Good morning, everybody. Today is the first day of the Harvard Data Science Conference. And the first event that we are having is a tutorial on causal inference. And we are really delighted to have Jose teaching the course. In addition of people sitting here in the room, there are several people also there join online. So there will be a double audience. So it is with my great pleasure, I wanted to introduce you, Jose. And Jose Zubizarreta is a professor in the Department of Healthcare Policy at Harvard Medical School. He has a joint appointment, very happy, my department, Department of Biostatistics at the Harvard School of Public Health. And he's also a faculty affiliate in the Department of Statistics at the Faculty of Art and Science at Harvard. He's very well known in causal inference. His work centers on the development of statistical methods for causal inference and impact evaluation to advance research in healthcare and public policy. Jose received his PhD in statistics at the Wharton School at the University of Pennsylvania in 2013. This is one of the departments where really has been the place where several of the ideas of causal inference started, focusing on optimal designs for observational studies using mathematical programming with application to healthcare policy. As he has a lot of awards, as I'm going to mention a few of them. Just as a doctoral student, he was honored with the J. Parker Memorial Burns Prize for Excellence in Research and the President Gutmann Leadership Award. He was a Fulbright Scholar and also received several Student and Young Investigators Award from the American Statistical Association, including awards from the Biometrics, Epidemiology, Health Policy Statistics, Social Statistics, Government Statistics, and Survey Research Method section of the American Statistics Association. He was also recipient of the Tom Tenhave Memorial Award for exceptionally creative or skillful research on causal inference at the Atlantic Causal Inference Conference. So that's why I have notes, because I can't possibly remember all of the ones he had. Now, he's serving currently as a co-editor of the Handbook of Matching and Weighting in Causal Inference by Chapman and Hall, and is an associate editor for Biometrics, the Journal of Computational Graphical Statistics and Observational Studies. Also, Jose teaches the graduate course design of experimental and non-experimental studies at the Faculty of Art and Sciences at Harvard University. So join me in welcoming Jose, and the floor is yours. Thank you for coming, Jose.
Thank you so much, Francesca, for having me. Thank you for being here. I'm very excited to be here with you today, sharing some ideas about this growing field of causal inference. This is a field that has grown exponentially over the last decades. There's a lot being done in statistics, biostatistics, computer science, economics, political science, and so on. And today I'm going to emphasize some ideas I think are central from the more classical statistical standpoint, emphasizing a lot experimental design, and that how defines how we approach, how we design and analyze observational studies. I have prepared these handouts with the main takeaways from today's talk. So I'll share them. If you could please have one and pass the rest. Similarly here, for me are kind of like the fourth ideas, the takeaways that I wish you take home today after today's talk. I'll start with some preliminaries, an introduction to causal inference, and then talk about the experimental ideal. The idea is that in observational studies, we always want to ask ourselves, how would that ideal experimental study be done at the time of designing and analyzing observation? Then we'll talk about the fundamental problem of observational studies, which is confounding. We'll have a break. And then I'm going to emphasize matching methodologies to see how they approximate certain features of randomized experiments. Talk a bit about instruments and discontinuities. So that's the roadmap. If you have questions, please stop me at any. Okay, so the goal of today's tutorial is to provide a conceptual basis of cause and effects, to emphasize what are the key assumptions needed to see these estimates, these parameters that we wish to learn from the data, from observed data, and understand the strengths and limitations of common approaches used for causal inference. namely matching, regression, and weighting, which are three fundamental methods which are kind of like building blocks of other more nuanced methods in causal. As I said, I'm going to focus on certain ideas from experimental design. Our mode of inference is going to be mostly randomization-based inference, as opposed to superpopulation-based inference, and I'm going to emphasize the use of matching. So this is a way to acknowledge that there are many perspectives in causal inference which emphasize other tools too, and they're complementary, okay? So for example, matching methods can be used in the design stage of an observational study to then use machine learning, all right? And I also wish to acknowledge how much work has been done while at Harvard by great researchers, titans, I would say. For example, William Cochran, who coined the term observational studies, Don Rubin with potential outcomes, Paul Rosenbaum with his thesis on design of observational studies and his joint work with Don Rubin on the propensity score, Jamie Robinson and Brad Rodnitsky, who recently won the equivalent of the Nobel Prize in statistics for their contributions to causal inference, and Hiro Invens, who now is no longer here, but he did amazing work when he was here too. And as you know, he won the Nobel Prize in economics for his work on causal. But there's also a lot today going on causal inference across the university, across many of its schools, FAS, the School of Education, Harvard Business School, the medical school, and so on. There are many professors and students working on causal inference. And I want to highlight this initiative led by Professor Francesca Dominici here, to bring together, to integrate, connect these different groups in the causal inference working group to enhance and connect those efforts. So for example, here we have Gary, Kosuke, and Matt working on political science, Luke Miratrix working in education on methods for causal inference, Yav and Edward McFarlane in business, in computer science in this building, Susan Murphy and Sham Kakare, and in health we have Miguel Hernan, Tyler, and their causal lab, which is this big initiative to do causal inference in the health science. So there's a lot going on causal inference in the university. We have this causal inference working group. Please sign up if you want to learn about the seminars and be part of this. And I also have to acknowledge support from the Sloan Foundation, who is funding this causal inference working group. And personally, I have to thank PCORI because it has funded my research on this idea. All right, so causal inference. As a statistician, I see statistics as this discipline which is at the juncture of mathematics and science. And in this juncture, in this interface, I see causal inference very much at the center of that. Causal inference to me is about learning what works, and more specifically for whom, when, and why. For whom pertains the question of effect modification or treatment effect heterogeneity, when the question of timing of treatment, and why the question of mediation. And some examples very relevant today are, for example, the effectiveness of COVID-19 vaccines against hospitalizations. Today, with the rising inflation, what is the effect of raising the base rate? And today, as a running example, we're going to use this example of the impact of a labor training program on earnings. But the point is that causal inference is pretty much everywhere in science. We want to learn what works. And causal inference, as you know, requires careful thinking. It requires integrating statistics, machine learning, data science with substance. Okay, the two have to go hand in hand. And I like very much this phrase from Cook, who said that in causal inference, we want to adopt this multiplicity strategy, this multiphasic attack, where we don't conduct one study, we conduct many of them, and we integrate the causal evidence from different studies in a way that the different studies, in the spirit of evidence factors in observational studies, as developed by Paul Rosenbaum, the different studies have different strengths and weaknesses. So that altogether, they rule out non-causal explanations and they support certain causal claims. So I would say that's where we're going, okay? And today in this tutorial, I'm going to emphasize some ideas to build one such study as well as possible, all right? So that is as transparent as possible, as optimal as possible in some ways, but ultimately we want to integrate evidence from many such. Just as we design experimental studies, we also design observational studies. There are many decisions that we make as researchers on observational data that have to be done very carefully. So we often think that because it's observational study, an observational data set, we just run a regression. No. There are many choices embedded in that routine practice of just running a model. And we have to be careful about it. And again, we want to integrate evidence from different. Another point that I wish to make is, as Rosenbaum says, causal inference is not about bigger data, it's about better. The way I see this is that the opportunity that big data offers to us to do causal inference is that on those big oceans of data, there are more corners where we can shed light into causal explanations, okay? But we have to be careful in using big data for causal inference because predictors are not the same as the cause. So we have to think very carefully about this. One of the main ideas in this tutorial is how key notation is when it comes to causal inference. Causal inference can be seen as this big effort of defining very clearly what we wish to learn from the data, under what assumptions we can actually see that from the data. And once that happens, after identification has happened, then the problem is pretty much like any estimation problem in statistics or machine learning, where we can emphasize some things or others, like efficiency or transparency, hopefully the two of them together. But causal inference happens very quickly, I think, in the problem, in the setup of the problem. And I would say then also very late in the stages of the study, integrate evidence, we do sensitivity analysis, and so on. But in this first part, notation is key. So what I'm going to do now is to introduce the potential outcomes framework by Niemann and Rubin. So as a running example, we're going to study the impact of a labor training program on earning. And suppose that we want to estimate the effects of a labor training program on a single individual, I. For this, we're going to define some notation. Some of you may be familiar with this. Yeah, by the way, how many of you have been exposed to potential outcomes? So many of you, like 60% here. But this is very important, okay? I want to be very clear about what is going on here. We're going to define these two outcomes, potential in the sense that they're counterfactual. yi1 is going to be the potential outcome for person I under treatment, yi0 the potential outcome under control. So in our example, yi1 is going to be the income that the I person would have if he participated in the program, and y0 otherwise. And as Holland famously said, we only get to see one of these two potential outcomes, right? Which is the fundamental problem of causal inference. Otherwise, this would be very easy. I just measured your potential outcome under treatment, then under control, and I get the contrast of the two, either by subtracting or by getting a ratio, something like that. But that's the difficulty. We cannot do it. Yeah, we only get to observe one state of the world. So what we do is to imagine these two stages of the world. And the question is under what conditions we can make progress, given that we only observe one realization. So as said, these individual effects are not observable. This or that. Given this, we have to put some assumptions on the problem in order to learn something that is causal. And to have a better picture here, I wish to show what Rubin calls the science table. I think this helps a lot to fix ideas, because this is what we would ideally have as investigators, okay? We don't, but we strive to get something like that, okay? And it's important to keep it in mind as this benchmark. So ideally, we would be these omniscient investigators, and we would see for every unit, 1 to 10, these are 10 people in our running example, we would see their earnings if they were to be assigned to control, and their earnings if they were to be assigned to treatment. Z is going to be our treatment assignment variable. So if Z is equals to 0, the outcome that I observe is the potential outcome under control. And what would be the effect of treatment on every individual is this last column here. It's the subtraction of these two variables, right? So for example, for unit 1, this individual effect is $799. The problem is that we get to see a data set that is like this, right? Where, of course, under control, we only get to see the potential outcomes under control. And analogously, under treatment, we get to see the potential outcomes under treatment. And we want to estimate these numbers ideally, or if we can't, settle for something else. If I cannot estimate the effect on you, I'm going to estimate the effect on a group of people. Okay? And that's what Holland called the statistical solution to the problem of causal inference. I'm going to let the law of large numbers kick in, okay? We're going to randomly assign subjects to treatment so that I can learn in a very precise way the average effect. So this statistical solution of causal inference is to randomly assign the treatment and estimate the average treatment. Here we have this matched pairs of similar individuals, and for each individual, flip a coin, they were assigned to treatment and control, and some nice things happen, which is the next thing that I want to explain very carefully. As we move to observational studies, these two features of randomized experiments have to be very clear. These two features, I'll explain them in a minute. So I said that notation is very important. I think the least notation that we can introduce to study this problem is this one. Again, our treatment assignment indicator set, our potential outcomes under control and treatment, and I get to see only one of the two of them. This is the observed outcome. So unit I is assigned to treatment, yi is equal to y1, okay? We're going to have a vector of observed covariates, which is everything that I can observe about you in the data set. And of course, it's going to be the source of concern, UI, that we don't get to measure everything. They're going to be this unobserved confound. And as a preview of what's coming next, we want to design our observational studies so that we can rule out or kind of quantify the influence that an unobserved covariate U would need to have on our point estimate that assume that adjusting for X is sufficient to explain away our significant effect. But we're not there yet. We're in randomized experiments, which are very important to fix ideas as we move to observational. A key assumption embedded in this notation is the SATBA assumption, the stable unit treatment value assumption, which says two things. And one is that the treatment effect on you depends on your treatment as opposed to the treatment that other people receive. So there's no interference, which clearly doesn't hold, for example, in vaccinations, right? But this notation is saying that to be. It's a notation that can be enhanced to accommodate those settings and study interference. But embedded in this notation, we're saying that. We're also saying that there are only two versions of the treatment, 1 and 0. Okay, there are not other versions. So those are two assumptions that are encoded in this notation, which are summarized by the so-called STATVA assumption or stable unit treatment value. Both of these assumptions can be relaxed, but to make progress, we're going to start assuming. And this potential outcome framework has been fundamental to develop the theory of causal inference as we know it today. It was originally introduced, my understanding is, in experimental studies by Niemann, and then extended by Rubin by observational studies, then further extended by Robbins and Hernan to longitudinal studies of treatment effects. And I like very much the way that Invens and Woolrich explain why this notation is so important. It's because it allows us to decouple two exercises. The exercise of identification from the one of estimation. So if we were just to run, for example, a regression on the observed data and call that estimated coefficient the treatment effect, we would be conflating things in a way in which the estimation procedure, there are many assumptions about how the world works that we don't necessarily want to use from the get. Okay, for example, linearity, normality, and so on. By using this potential outcome framework, we can separate the exercises of seeing the parameters from the observed data from estimating them in different ways that have different strengths and weaknesses. If you want to use linear regression, great. But that is key about this notation. In your notes, I like very much this quote by Rosenbaum that says that a rigorous solution is preceded by a precise statement of the problem. This is what causal inference is buying us. This is what the potential outcomes framework is buying us. So notation is very, very important. And why experiments are the gold standard for causal inference? As your note says, it's because of two things. We often emphasize one of them, but I want to emphasize two things as we move to observational studies. It's very important for statistical control, confounding, and also for statistical inference. Okay? Randomization provides a basis for inference. That's what I want to explain next. All right? So what is wonderful about randomized experiments is that randomization is fair, it's just, it's equitable. It tends to produce two groups that are similar in expectation in terms of observed and unobserved covariates, but more precisely in terms of the potential outcome. It tends to balance their potential outcome. Hence, by taking averages, we can unbiasedly estimate the average effect of treatment. An intuitive way of seeing part of this is this so-called table 1 for covariate balance, where after randomization, we have that the treated and the control groups have similar means in their observed covariate. So for example, age is similar between the treatment and the control group just because of randomization. And as the sample sizes grow larger, because of the law of large numbers, these numbers tend to be more and more similar. So randomization is wonderful because it produces an unbiased estimator by design, by construction. That means that the investigator did something, and he knows because of that, that the estimator has certain properties, as opposed to assuming that was. So both observed and unobserved covariates, the potential outcomes also, are balancing expectation across treatment. And randomization is also going to allow us to do inference without making any distributional assumption. This is what is called the reason basis for inference. So more formally, I want to explain what this business of identification is about with perhaps the most basic parameter we can estimate, the average treatment effect. So randomization guarantees that. What is that? This is the mathematical symbol for independence from Phil David. And it says that the potential outcomes under treatment and control are independent of treatment assignment. An intuitive way of thinking about this is that Z cannot predict your potential outcomes. Another business are your observed outcomes. And that the distributions of these two objects are going to be the same across values of Z. I like very much this way of putting it, which is that a fair coin knows nothing about the individual units and is impartial in its treatment assignment. And as a result of this is that we can see this causal estimate from the observed data. This is what we call identification, okay? After we get this, we can do estimation. The question is going to be how we compute these objects from the data. But the problem is that when we start from here, we don't get to see this in the real world, right? Because by linearity of expectation, we have the first equality, right? And the problem is that this second term here, we never get to observe it, right? The first term is easy because under treatment, I see the potential outcome under treatment. So I can just replace the potential outcome under treatment for the observed outcome, right? This is what happened here. And I can just compute that from the data. For example, by taking a simple average in the treatment. The problem is that in this term here, under treatment, I don't get to see the potential outcomes under control, right? So that's the problematic term here in randomized experiments. But because of randomization, because I have that independence assumption and that the distributions of the potential outcomes are the same under treatment and under control, and therefore, in particular, their means are the same under treatment and under control, I can just flip this, right? And this is something that I can see from the data. So what happened here is that we use linearity of expectations and then randomization. And this was not an assumption, it's something that we did. We physically or via our computer, we randomly assign subjects to treatment under time. So we have a very strong justification to and then we can estimate these parameters in different ways, for example, via regression, via weighting, just by taking simple average. Okay, but this is the role of randomization for statistical control. And we also have the same thing if we wish to estimate the overall treatment effect. An intuitive way of thinking about this is because the treatment sample is a representative sample because of randomization of the overall sample to estimate the average treatment effect on the whole group. So that's wonderful about randomization. But there's a second thing that is wonderful, which is less emphasized typically when we're introduced to causal. And that is the role of randomization for exact inference. And that means that randomization physically induces a distribution that can be used for exact testing without any normality assumptions whatsoever. To see this, we're going to consider this sharp null hypothesis by Fisher, which is the most basic question I would say we can ask to a data set. The question is, H naught said that there's no effect for no one, okay, as opposed to saying there's no average effect between groups. So the way we can use randomization to test this is as follows. But I think that a very fruitful way to think about this is to think as hypothesis testing, as a proof by contradiction, but that has a stochastic element, right? So in a proof by contradiction, as you know from math, we start by making a statement that we presume is true. We push through the logic of our assumptions, and then we arrive to a conclusion that it's contradictory. If that's the case, it must be that our initial statement was wrong. So that's exactly what we're going to do here with hypothesis. We're going to start by stating this. There's no effect on anyone. And we're going to contrast that statement to the evidence provided by the data as summarized by a summary statistic, by a test. All right? So in this stochastic proof by contradiction, we're going to assume that H not holds, that the null hypothesis of no treatment effect is true. Okay? Then we're going to consider all the set of possible treatment assignments, omega, which we can compute. In big experiments, it's going to be a thankless task because there are many possible such combinations. But in small experiments, we can actually compute that in closed forms, in an exact. And then we're going to have our test statistic, which can be the difference in means, but it can be something more robust as a way of summarizing the data. And we're going to ask, how likely is, under all possible randomizations, to obtain a value of the test statistics that is this or more extreme? If that probability is very, very low, that is evidence that there's something wrong with H naught. Okay, so this was a very extreme out, right? So we're going to use that to compute a p-value and under a given level, reject or not the null hypothesis of no treatment. Why this is important? I think it's important because we're making this effort to have minimal assumptions in our analysis of randomized experiments. And then when we move to observational studies, we would like to have a theory and a methodology where these notions also play a role. In particular, when we move to the question of unmeasured confounding, right? So by the end of today's tutorial, I'm going to discuss a model for sensitivity analysis, where the observational study can be seen as a general case that embeds a randomized experiment, where there's no uncertainty in treatment. There's a question.
Trying to understand a little bit more of like point number 2, which is like the set of possible treatments, omega, from where Z was selected. So in my head, at least, like if someone is receiving a treatment, like you already know what Z is, right? So how are you like testing like a whole possible set from whether
Yes,
is given?
That's a great question. And to fix ideas, let me walk through each of these steps next. Okay, that's a great question. So to answer your question, we're going to consider a randomized experiment with 5 matched pairs. Okay, so first I match people that look alike from both sides of the room, and then I flip coins. Okay. This is one possible realization of the treatment assignment mechanism. Another one is this one, where I just flip the first pair. Okay, and this is another one, and so on. There are 2 to the 5 or 32 possible treatments, right? So our data set is going to look like this. We're going to have these 5 matched pairs. In each pair, of course, there's a treated individual and a control individual. And because they were matched before randomization, they have similar covariates, age, and these indicators for rate. And these are the outcomes that we observe, earning. And delta Y is the difference in outcomes within match. So we assume that H not holds. To fix ideas here, we see, for example, what is happening in pair 1. the difference in incomes is 1,456. Okay. Step number 2 was to consider the set of possible treatment assignments. This is one possible treatment assignment where the first individual in each match pair was assigned to treatment. Okay, that's what this row of ones means. But another one is where in pair 5, it was the second individual who received treatment. And I said there were 2 to the 5 possible treatment assignments. Yeah, these are all of them. Okay. And the point is that for all these possible treatment assignments, I can compute the value of the test statistic. So for example, if I'm using the difference in means, it's going to be these values here. So remember that under the sharp null, treatment has no effect. So all what randomization is doing within pairs is flipping the sign of the unit, of the pairs to be precise. Okay, so this is what's going on in this table. Here you can see in row 1 and row 2, the only difference is the sign of delta y5, right? So under all these possible realizations, we can compute the difference in means. And remember that the first row was what I observed from the data. That was the realization of the randomized experiment that I got. And the question is that strong evidence against the sharp null hypothesis of no treatment? To answer that question, we can simply count. We can see across this distribution how likely is to get a value of the test statistics that has that value or higher, right? So this is the value that we got, but it could have been another one. And across all these rows, we're going to compute the probability of having a value of the test statistic that is at least that extreme. Because this is a randomized experiment where we had equal probabilities of assignment, each row has the same probability of 0.03, right? And then we can compute the probability of seeing a value of the test statistic that has this value or higher, which is 19%. And by the usual levels, a 5% significance, we would conclude that this is not strong evidence against the sharp null hypothesis of no treatment. But what I find very beautiful about this is that we tested without any assumptions. We just used this thing that we know we did, which is that we're flipping coins, right? We use random assignment for exactness. We didn't assume any notion of a population here either. We were making inference just for the sample. You can also have that other layer of uncertainty where you also have a random sample from a population. And what is very important, as we have emphasized, is that here probability enters the experiment only through the random assignment, which is controlled by us, the experiment. And these ideas, in some theories for observational studies, can play a very precise role. And that's what I would like to emphasize in the next part. So now we're going to move to observational studies. So to be clear, we would ideally answer most of the questions that we have in real life using an experiment, right? But oftentimes we can't, okay? Because randomization is infeasible or unethical, yeah, we have to rely on observation. And here we want to ask again, what would have been that ideal experiment we would have done? Why is that? Because the law of large numbers ensures that treatment and control are comparable. And again, that randomization is a ticket for in a very precise exact. So if a randomized experiment looks like this, an observational study looks like that, not only the groups have different sizes, but we can see that their compositions are different. Proportionally here, we have more females, you know. So we can see that they're different in terms of attributes that we can observe, and likely in attributes that we do not observe. And those differences can confound the effect of treatment. So we need to do something about it. We're going to distinguish between two sources of biases in observation. First, we're going to say that an observational study is biased if the treated and control groups differ before treatment in ways that matter for the outcome. Overt biases are biases due to variables that we can observe in the data. For example, age or education, we typically measure that in the data, and we can adjust for that. But the big question is about hidden bias. It's about those variables that we cannot measure. For example, in our labor training example, and whether, for example, ability or the motivation of the workers is really what is driving differences in incomes as opposed to treatment assignment. Okay. And we want to distinguish between these two sources of biases to take care of the first source of bias in a very transparent way, without making strong assumptions, parametric assumptions, without extrapolating if possible, and also in a way that then we can make statements about the second source of bias, about hidden bias. Right? And matching can help us to do that. It's not the only way of doing it, but it can help us to take care of these two tasks. And at a high level, we're going to discuss two strategies, two identification strategies. Again, an identification strategy are those set of assumptions that allow us to see the causal parameters from the observed data. The most common one is known measure confounding. So there are some strategies that control for overt biases by adjusting or balancing, as we say, covariates. And there are other strategies which, for example, like instrumental variables, which control for that variation in a different way. They don't explicitly balance covariates, but they use some variables or type design features where that we think happens, where you have set balance in those other attributes. So the question that is going to guide us here is this question by Cochrane, that the planner of an observational study should always ask himself, herself the question, how would the study be conducted if it were possible to do it by control experimentation? And for this, we're going to use matching. The basic question is, under what conditions, adjusting for those things that I can see in the data set about you, about each of us, are enough to remove bias? For this, we're going to consider an outcome variable y, a treatment indicator z, and again, observed covariates x. And we're going to assume that x, the vector of observed covariates, include all the variables that are associated both with the treatment assignment and the potential outcome. The intuition is that for individuals with similar values of x, treatment assignment is as if random. That's the basic intuition. If I have subjects with the same age, education, earnings before the treatment, then treatment assignment is haphazard, is as if it was randomized. And this is encoded by this assumption here, which is the same one as before, but now conditioned on x. The intuition is that in the cells defined by x, we have this little randomized experiment. So conditioning on all the facts that I know about you or you, treatment assignment is essentially at random. Conditioning on all the facts that I know about you, the distributions of the potential outcomes under treatment and control are the same, in particular the mean, which is again what we're going to use for identification. And this is an assumption that is often used in practice that has different names in different literatures. In statistics, we call it ignorability. In economics, I think it's called selection of observables or exogeneity. In the missing data literature, it's called missing at random. But in essence, it's the same idea. So that's one assumption we're going to make. And the other one is this overlap assumption, which is necessary for making what is called nonparametric identification of the average treatment. So that without relying on any functional form, we can see those parameters in the data. And for this, we need every individual in the data set to have a non-deterministic mechanism of receiving treatment or control, so that they could have been assigned to treatment or control. So the probability of being assigned to treatment, given the observed covariates, is bounded away from 0 and 1. And with those assumptions, we can see this parameter. We can identify. This is the average treatment effect on the treated. Again, by linearity of expectations, we have this first equality here. The problem is this term here, which we cannot observe, right? So what do? We're going to do basically the same thing as before, but with one additional, which is this one here. These rules are very important because they tend to appear in different causal inference problems. So I think it's very important to fix this idea. So again, we cannot see this under treatment. What we're going to do first is to use the law of iterated expectations or the tower property. Going to condition an x here and then take the average over all the x. Why are we going to do this? Because once I have x here, I can invoke the unconfoundedness. That says that even everything that I observe about you, I cannot predict your potential outcomes under treatment or under control. The distributions are the same, the means are the same. I can just flip this. And then by consistency, under control, we get to see the potential outcome under control. I can replace this by the observed outcome. And this is a quantity that we can just compute from the data, and that we can compute in different ways. One natural way of doing this is by computing the sample analog of which for this, we're going to define this regression function, the mean potential outcome under treatment level set, given the covariates x's, which under the unconfoundedness assumption, we can write like this for the observed outcome. And this term here can be estimated by using this estimator, like, which is an estimator where we are predicting the potential outcome under control for each individual in the treated sample, and we're taking the average over the treated sample. Okay. So this suggests this term here suggests using an estimator like this one. And the most basic thought, for example, is to use linear regression for this. Okay. But there can be issues with that. So in our earning example, in our labor training example, imagine we have a situation like this, where in truth, earnings under treatment are generated by this curve here. And imagine that earnings under control are generated by a curve like this here. And that the data that we get to observe is that for higher earnings, we get to see more of the treated subjects, and for the controls, we get to see lower. If we were to use linear regression to estimate the average effect of treatment, in its most basic form, we would fit lines that look like this, right? And we can see here that we would be overestimating the effect of treatment on the controls, and similarly, here we would be underestimating. As a whole, we would be underestimating what is the effect of treatment. What is going on here is that we are misspecifying the regression model when we have limited overlap in power distribution. And by doing that, we can get a wrong effect estimate. So potential lack of overlap in the covariate distributions between the treatment and the control groups, and misspecification of the outcome models can produce bias in our effect estimate. Also, coming back to the idea of the experiment, one can argue that one wants to do the adjustments in a way that mimics, that resembles what we're doing in an observational study. Sorry, in an experimental study, where the everything that has to do with the design of the study doesn't require touching the outcome. Okay. And in routine use of regression, we can miss. And other questions are how these linear regression adjustments are emulating certain key features of a randomized experiment. So the point was that estimating this object motivates doing something like that. It's the natural impulse. And if we were to use something like a linear regression, when there's limited overlap in covariate distributions, we can easily get it wrong. In addition, we want to do the adjustments in a way that is similar to what we do in experiments without looking at the outcomes. And then I would argue that there are other questions about which we want to be transparent with our methodology for causal inference. Specifically, how the procedure is emulating certain features of randomized experiments, like the one of covariate balance, in order to isolate the average effect of treatment relative to a specific population. So with some procedures, this is not very clear, and I want to come back to this. All right? Matching has advantages and disadvantages. A disadvantage that it has is that it tends to be less efficient than, for example, weighting methods. But from the standpoint of shedding light on these questions and transparency, I think it has some very strong attributes. All right? So that's something that I wish to explain more carefully. So now we're going to talk about matching methods to approximate a randomized experiment. So again, this is the experimental ideal. This is how we would like things to look, but sadly they don't. We have to work with this observational data set. So what we're trying to do with matching, the intuition is as follows, is that this is our observational data set, which differs in terms of variables that we can observe and not. What matching is trying to do is to find this randomized experiment that is hidden inside the observational study. In its simplest form is using pair matching to find individuals one-to-one that are similar in terms of observed covariance, in such a way that we balance covariance, that we have this table 1 for covariance. So some positive features about matching as a methodology is that it's simple. While they can be complicated algorithmically, at the end of the day, the structure of the data set is very simple. We have these match pairs, for example, where it's very clear what we are comparing to what, this apples to apples comparison, if you want, where we're keeping the unit of analysis intact. So that means that in the data set after matching, you are going to continue being you in the data set, as opposed to a possibly non-convex combination of people, like which can aid intuition and help some tasks, like, for example, collecting more information about the units at hand. Another feature is to avoid what we had in that toy example with the red and the blue curve, which is that we want the adjustments to avoid extrapolating from where we do not have data. We want our point estimates to be a result of an interpolation of the data that we observe, as opposed to an extrapolation that goes very far away from the data that we do have. Then the other point was that we want to do the adjustments in such a way that we are not looking at the outcomes, so that we blind ourselves and we have the possibility of being objective and not affect the levels of the test. We also want, and this methodology can be used with other strategies like instrumental variables and discontinuity designs, and it facilitates, again, the sensitivity analysis that we're going to discuss later. And I have to acknowledge that there's a very vast literature on matching methods. For example, the literature on nearest neighbor matching, optimal matching, coarse and exact matching, and so on. The one that I'm going to discuss today is one that we have been developing over the last 10 years or so with co-authors, where we're going to leverage certain tools from mathematical programming to approximate that experiment in the best possible way in terms of covariate balance, sample size, representativeness, and so on, because we're going to directly optimize forward. Okay. So to fix ideas, ideally, the way that we would adjust for covariates is to exact match by everything that I observe in the data. So I would match a female to a female and a male to a male, and so on. So again, if I have one covariate, I match a female to a female. If I have two covariates, okay, a young person to an old person, and so on and so forth. Ideally, the way that we would adjust for covariates is by building these bins, and within cells, within values of these bins, people are exactly the same in terms of observed covariates. But very quickly, we see that with many covariates, with two covariates, we have 4 types of units. With 3, we have 8 types of units. With 4, we have 16. With 5, 32, and so on. And with 20 covariates only, we have over 1 million types of units. So 2 to the 20 is more than 1 million. The point being that in typical data sets, which have a lot more than 20 covariates, because we also have continuous covariates, we cannot afford to match exactly for everything. So for the typical data set, in healthcare, for example, in CMS data sets, there are just not enough people on Earth to match exactly for everything. So it's the ideal form of adjustment that we would pursue, but it's impossible because there's this curse of dimensionality in exact match. So we have to do something else. So ideally, we would do this. Ideally, we would do this in addition to something else. But there's this fundamental limitation. So a thought to make progress is that randomization didn't bias exact matches. We saw on our sketches about randomized experiments that randomization tends to produce balance on aggregate, not exactly in every possible way. And a fundamental tool to construct matched data sets that are balanced in aggregate is the propensity score, which is the conditional probability of treatment assignment given the observed covariates. Not given the unobserved covariates and the observed covariates, it's just the observed covariates. And the propensity score this conditional probability of receiving treatment given the observed covariates has some wonderful property. Basically, is that by adjusting for the propensity score, by matching on the propensity score, we tend to balance all the covariates used to estimate the score. Not the unobserved covariates, just the observed covariates. It tends to balance all of them, just like randomization tends to balance, well, everything. But here the propensity score balances the observed covariates in expectation. And it's very handy because it's this one number. It also says that by acting on this number, I have this guarantee on all the other numbers, all the other individuals. So it's a very helpful tool in that way. It's also a very helpful tool conceptually when we do math about different estimates. The propensity score tends to appear in different representations of the estimate. It's kind of like this number that it always appears, and the question is how we estimate it directly by modeling the propensity score, by imposing balancing conditions, the two of them, and so on. So based on the propensity score, we can do matching. For example, we can build this distance between each treated unit C and each control C on the estimated propensity score, on the propensity score scale or the logit scale, in such a way that then, based on this distance, I match units that are similar in terms of the propensity score. We can also use the propensity score as what it's called a caliper. That means that if you're close on the metric of the propensity score, then we use another distance, which can be like a Mahalanobis. And using any of these distances, they're the covariate distances, and they're the algorithms that we use based on these distances to match. And there are different classes of algorithms. We can talk about optimal algorithms. We can talk about algorithms that are not optimal, but that perhaps are very fast or easy to implement, like, for example, nearest neighbor matching, where what we do is basically to sort individuals based on the estimated propensity score, and then match each control or each treated subject to the closest control, one at a time, but one at a time. So making the best decision first, one at a time, as opposed to doing it globally. And of course, we can have the optimal version of that, where instead of making these greedy decisions one at a time, we optimize as a whole the distances between units to find our match, which is what is called optimal matching. So optimal matching finds an assignment between treated and control units that minimizes this global optimum, which is usually the total sum of covariate distance. And by doing this, we have these theorems by Rosenbaum and Rubin that say that by matching on the estimated propensity score, I tend to balance the observed covariate. Now, a difficulty with that is that that result is predicated on two things. In practice, it's not that easy to actually balance the covariate. For example, if my sample size are relatively small, or the complexity of the covariates is too high for the size of the data, then balancing those covariates can be very difficult. Even if I estimate correctly the propensity score. And of course, in practice, we never know whether we're estimating correctly the propensity score, so there can be a lot of iteration in balancing the covariate. So we're going to try to deal with that, okay? So that we can obtain better balance by designing, by construction, in which the investigator, just like in an experiment, has this design, and he randomizes to have this design, including balance and others. Here, we're going to directly balance certain features of the covariate. And for this, we're going to use this matching framework, which in a sense encompasses a different matching approach. We're going to solve this generic optimization problem where in the objective function, we're going to have two terms that compete with each other. We're going to minimize over a vector of match assignments. The vector M says who's matched to whom. These two terms that compete in the sense that they pull in different directions. One term wants to minimize the total sum of covariate distances between match units, for example, the propensity score. And the other one wants to do it while using as many units as possible from the data in order to allow for the fact that sometimes the groups are too different and you just cannot match everyone. There's some units that have to go in order to balance the covariates relative to a population of interest. Okay, so there's a trade-off between the two, which is going to be governed by this parameter lambda. And then we're going to solve this objective function subject to certain constraints, which are going to enforce a matching structure, for example, one-to-one matching, but it can be something else, certain balancing constraints, for example, balance the means or the marginal distributions, or in principle, the joints, if the data allows for that, and certain representativeness constraints so that the samples are not only balanced relative to each other, but relative towards a population that we care about. Okay, a target population that is of substantive interest. That is more or less the framework. And there's some specific cases here that are familiar to us. For example, optimal matching is when we just have the distance and the matching constraint. There's another instance of this problem that I find very valuable, which is called cardinality matching, where there are no distances, but knowing that there's limited overlap in covariate distributions, we're going to find the largest match study that is balanced and representative towards a target population, but that again, that it's as large as possible, trying to maximize the efficiency of our estimator at the end, subject to the matching structure on the data. So these are two cases, and I think these two cases are relevant because in step one, we can do cardinality matching for balance in aggregate, and after matching for balance in aggregate, we can solve the optimal matching problem to emphasize distances between match. Okay. So the way this is going to go is that, well, if with usual propensity score matching methods, there's a lot of iteration in balancing covariates. We have this step 0, where we first define what are our standards for balance, and then we repeat these 4 steps, where first we estimate the propensity score, then we trim observations based on the estimated propensity score, then we match on the propensity score, and then we check balance. But the point is that there can be a lot of iteration until we meet the standards of step 0, because we're not directly targeting balance, because the propensity score can be misspecified, or it's just too complicated in that data set to balance everything, relying on the law of large numbers. Okay, there can be a lot of iteration here. So instead of doing this, we're going to solve this other pseudo algorithm where step 0 is the same, but we're going to directly maximize the size of the match study. Something that is very much in the spirit of what Cochrane suggested, that in designing an observational study, we want to select samples of study that are as large as possible so that we can estimate effects of practical size, but at the same time, adjusting for potential confounders. And in this task, using both the statistician and the subject matter expert knowledge in designing the study. The idea is that through the constraints of cardinality matching, that subject matter knowledge comes in, what we balance and to what extent. And we're going to find the largest study that is balancing those. And this is a natural moment to stop so that then we can see how these ideas work in practice using ARC. So let's take a 15-minute break and resume at 10:30. We were discussing matching as a methodology, a general methodology to approximate aspects of randomized experiments, most saliently balance on covariates. And when it comes to covariate balance, we can enforce different forms of balancing distributions. It can go from exact matching, where, as we were saying, is the ideal way of matching. We exact match for every category of the covariates, to balancing the means of the covariates, which is often what is reported in many clinical trials. But there are reasons to balance covariates better than just the means. Ultimately, what justifies a form of covariate balance is a theory for the outcome model. If the model in truth is linear, the unknown outcome model is linear, then balancing means is enough. If the model is additive, then we want to balance the marginal distribution. And the point is that we don't know how's that model. We want to balance covariates in a way that it's robust to be specifying that class of model. So that's a bit of a framework to think about covariate balance. And we're going to discuss how to use this package that we wrote called Design Match for R, which you can download for CRAN. Recently, we built a Docker with the help from CCD at the medical school so that installation is more easy. I can share the code with you. We have this tutorial that we're going to discuss. Where first we're going to install this package Design Match, which follows this framework here that I was telling you. And where different instances of this matching problem can be implemented and solved by using different functions in the package. So if you go to the help file, here you're going to see a description of the different methods. And something that it's important to highlight is that the performance of this package depends heavily on which optimization solver you use running on the back. By default, we have GLPK running on the back, which is free for everyone. It's a good solver, but a much more powerful solver is Gurobi, which is free for academic users, but not otherwise. And we have some installation instructions to install it. We're going to first read some auxiliary functions that we're going to need to run this code. And we're going to use, as I was saying, this running example from a labor training program, the Lalonde example. So I'm going to load here the data. So here I have attached the data. And I'm going to briefly describe the data set so that we have a sense of how it looks like. I guess I'm going to move this a bit up so that it's not in the corner of your screens. Okay, so in this data set, we have 185 treated units and 429 controls. And these are the variables that we have. We have age, education, these indicators for race, merit, educational degree, and these are the earnings before the treatment, the labor training program, and this is the earning after the labor training program. And I'd like us to take a look at the distribution of these variables before any adjustments. And what we see here in this column here, mean T and mean C, are the means of these variables before any adjustment, how they look in the treatment and the control group. And we can see, for example, that the control is slightly older. The control group is slightly older. It has 28 years as opposed to nearly 26. We also see a big difference here in these indicators for race Black and also race Hispanic. And we also have these differences in earnings before adjustment. So if we were just to estimate the average effect of treatment by taking the difference in means between these two groups, that's likely going to be confounded by these variables which are relevant, right? We would think that race, education, the earnings before the labor training program have an impact on subsequent earnings, right? So we want to adjust for that. And what we're going to do first is to solve an optimal matching problem where we're going to minimize the total sum of distances in aggregate between the treatment and the control group using a version of the Mahalanobis distance, which is robust to outlier. It's one of the distances I was showing you in the slide. That kind of like longer equation is this distance here. So using all the treated observations, we're going to find an optimal pair matching that minimizes the total sum of covariate distances between matched pairs using this rank-based Mahalanobis distance. And then we're going to check balance. And for this, we're going to define our treatment assignment indicator, which has to be sorted. The data set has to be sorted in such a way that first we have the treated subjects and then the controls. That's important when you use these functions. We're going to define our matrix of covariates, age, education, and so on. And now we're going to define our distance matrix, the matrix with the delta TCs. Remember the distance between each treated unit and each possible control. And for this, we're going to use a function that we have called distmat, where the arguments are the treatment indicator that I showed you before, also the matrix of covariates, and then we're going to round this to 2 digits of decimal. And this distance matrix has 185 rows and 429 columns for the treated and the control subjects. And to have a sense of how it looks like, here we're showing the first 5 times 5 elements of the matrix. So this says that the covariate distance between treated unit 1 and control 1, which in the data set has the number 186, is 1.23. So here the closest control to unit 1 from these 5 units would be this one here. It has the lowest distance, 0.99. And we want to find a match such that we find the closest match in terms of distances all together at a time, not one unit at a time. For this, we're going to define some additional parameters. We are not, these parameters is to subset the observations if there's limited overlap in covariate distributions. In other words, not to use all the treated subjects. We're going to do pair matching, matching all the pairs. And here we define the solver options. I'm going to use Gurobi, which is, as I said, the faster one. And we're going to use this function called bmatch, which is kind of a generic function that then we're going to instantiate when we do cardinality matching, optimal matching, and so on. Bmatch is the short for bipartite match, as opposed to non-bipartite match. So it's going to be bipartite in the sense that to begin, there are going to be 2 groups with different labels in terms of treated and control. We're going to find the match of treated and control units that is optimal in some sense. In non-bipartite matching, which is another function that we don't have 2 groups to begin. We have one general group, and we want to find close pairs so that then we add the label. in the context of an experiment by randomly assigning subjects to treatment and control. So there's B match and N match. B match for matching in observational studies, for example. And this function B match has many arguments. For optimal matching, which is what we're doing here, we need the treatment indicator, the distance matrix, and to say how many subjects we want to match, how many pairs, and the solver. And we run this by doing this. Okay, I have an error because I didn't run this part, I think. And we can see from this message here that the matching problem was built. We were using Gurobi as opposed to Cplex or GLPK, and that we found the optimal matches. So what we did here was to find an optimal match in terms of covariate distances. These are the indexes of the treated units and match controls. Since we're matching all the treated subjects, we can see that these indexes go from 1 to 185, that the corresponding match controls are these ones here. So for example, treated unit 1 was matched to control 593. Treated unit 2 was matched to control 551, and so on. And that we indeed match all the treated subjects, the 185 of them, in such a way to minimize the total sum of distances between match pairs. And that distance was in total 41.26. And we match these aggregate distances in order to balance covariates. So we're going to check balance. And here we have our table 1 for covariate balance. And we see, for example, in this covariate age, that it's relatively well balanced, education is much better, but we see for other covariates like married here, and this indicator here, for race, where some substantial imbalances remain. And the question is, how come? We did something that it's optimal, nonetheless, I'm not getting the answer that we desired. And what is happening is what we were discussing before, basically that by balancing on this aggregate measure of covariate balance, we are not necessarily balancing the components of that measure in any given data set, in any given realization of the data generating mechanism. Okay? Again, these forms of balance rely on the law of large numbers. This is perhaps not kicking in, or perhaps I misspecified the distance in some way. So the way we would proceed from here in order to improve this, for example, with propensity score matching approaches, would be to specify the distance in another way, emphasizing, for example, this covariate here black in some way, also emphasizing married in some way, you know, so that it improves balance. But there can be a lot of iteration. What we're going to do instead is to directly target such forms of such imbalances, again by using the B match function as follows. Okay. So here, using all the treated observations, we're going to find a pair matching that minimizes the total sum of covariate distances between matched pairs subject to constraints on mean balance. And then we're going to check balance. Yes?
How do you know that black is relevant to the outcome?
That's a really good question. So there's an imbalance in covariate black. The question is, does that matter? Typically, when we build these match samples, or when we do weighting, or when we specify a regression model, we rely on some theory about the outcomes. For example, in my department, where I work with doctors, we sit together with the doctors. They know stuff about the treatment assignment, which ones are potential confounders. We try to balance those. So typically, we rely on that substantive knowledge about the outcomes, which tends to come from, for example, from their experience. Other people try to learn that from the data, but I have to acknowledge that this is the difficult part of the problem. So what is really a confounder and exactly how I should adjust for confound. We conjecture that. So if I were not to include this in my journal submission, likely a reviewer would complain about it, as well as other variables, you know? We think it matters, but it's a valid question. Okay, so now we're going to use B-match to directly balance covariates. Everything is basically the same, but now in this part of the code, I'm going to specify variables for which I'm going to directly balance the covariates. I'm going to directly balance the mean of age, education, and so on in such a way that the imbalances in means are at most 0.1 standardized difference. Okay? I am going to match all the treated subjects. Again, I'm going to use the same solver. And I'm going to run B-match again. But now the only difference is that I have this MOM option. Is for moment balance. I'm going to balance the moments of these covariates, the means in particular. Okay? So I run the same code. We got the optimal matches. I'm going to get the indexes again. And now, let me see again. We matched everyone, but now the controls that are matched to the treated subjects are not exactly the same. And we're going to see this from these summaries here. Okay, now the distance is 40.4. And here we can see that the standardized differences are all smaller than 0.1, which is usually considered a good measure for covariate balance. Right? So we can see that here we balance covariates by construction with targeted. Right? Yes? But you have realized that I cheated, right? I didn't include all the covariates here. You realize that I didn't include this indicator for black in MOMCOVs. And the reason I didn't do it is, okay, let's do it. So let's see what happens if I include it. I'm going to do the same thing, but now this variable is here. This was a variable that was very imbalanced between the treatment and the control. Everything is going to be the same. I'm going to run this. And I get this message that says that the problem is infeasible. What is happening here is that I'm asking too much from the data I have. I'm asking to balance all the covariates in a very precise way without dropping any treated observation. And that problem is infeasible for the data at hand. A solution doesn't exist. You cannot do that. You either have to relax the balancing constraints or you have to drop some observation. But the point that I want to make in contrasting methodologies is that when you're not targeting covariate balance, you never know if you're getting an infeasible problem, you're not getting the answer that you want because you're misspecifying the propensity score, or because in truth in the data set, that solution does not exist. So you can be looking and looking and looking and looking for an answer when that answer does not exist. Okay, so I take this as good news. It's a sad fact about the data, but it is the data set that we have. And now we have to make decisions. One decision is whether we want to relax the adjustment, whether we really want to ask whether that covariate matters or not, as you were saying, whether I want to allow for greater imbalances in that covariate, or whether I'm willing to subset my analysis in some way that I estimate a more local parameter, something that is not the average treatment effect on all the treated subjects, but perhaps on a subset of them, which has that subset that has a good counterpart in the control. Okay, that is what is often called moving the target, changing the estimate. And there's an argument to be made that that's preferable than studying a more general parameter, but under stronger assumptions that they're harder to validate. Like, for example, race matters in this way, as specified by this specific model, we don't really know. Okay, so there's a trade-off here. But again, the point that I want to highlight is that by directly targeting balance, you know whether your data can support those forms of adjustment or not. So now we're going to solve a cardinality matching problem where we're going to allow to subset the units, but in a way that is optimal. Optimal in the sense that we're going to find the largest possible match study that is balanced as required by the investigator. So we're going to find the largest sample of match pairs for which all the covariates are balanced up to 0.1 standardized difference in means. And then we're going to check balance and see how many match pairs we obtain. In the first problem, we obtained 185. The question is how many match pairs we can obtain if we want to adjust the covariates up to this level, 0.1 standardized differences in mean. All right? So everything is the same, except for, except for three important things. Now we don't have a distance matrix. Now we're just finding the largest possible study. We're not going to match pairs in a first stage, just finding the largest possible balance study. We're going to subset the observations, and we're not going to require the number of pairs to be a specific number. We want it to be as large as possible, subject to the balancing constraint. And the balancing constraints say that the means have to be at most 0.1 standardized difference away from each other. This is a relevant point because then we're going to talk about representativeness. Here we're going to obtain two samples that are similar to each other, but in truth we want more. We want these samples to be similar to each other and to a population that we care about, so that our inferences are more generalizable to the population that we truly care about. So the distance matrix is null. The subset weight, now it has a value, 1. It can be whatever because the distance matrix is null. And total groups is null, the total number of match groups. I'm going to select all this. And then I'm going to use the function beam. So it's building the matching problem, it's using Gurobi. Now it's taking a bit longer to find the solution. It found the solution. And now let's get the indexes of match units. And now we see that we're matching only 120 match pairs. Initially, we were matching 185, but balance was not good. This is saying that the largest match pair study that you can obtain from this data set, balancing all the means of the covariates up to that extent, it has 120 units. And then we check balance here, and we see that all the standardized differences are below the threshold that we define. This is a usual threshold used in the literature for very long, 0.1, but it can be a different one. Actually, the threshold, it's quite questionable. It's the one often used in practice. But ultimately, what is happening here is that we're trading bias for variance between balance and samples. right? So there's a bias variance trade-off that is governed by the degree of approximate covariance. So here we have used cardinality matching to find the largest study of matched pairs for which the means are balanced. But the question here is, who are these folks here? This is not the sample of treated subjects. It's not the sample of control subjects. It's not the overall sample. This is a sample of subjects that I could match, that they are comparable. But they may not be a relevant sample towards in comparison to a population for which I really want to learn about. The structure of this sample may be very different to the one of a population that is more meaningful from a policy standpoint. So then the question is how to do this. And to do that, we could use the function bmatch, but here I'm going to introduce a new function called cardmatch, which also solves a cardinality matching problem, but that we optimize to handle bigger data. So if you want to use cardinality matching, I would suggest using cardmatch because it scales way better to large data. We have been able to solve match problems with several hundreds of thousands of observations in minutes. So it's quite scalable, which, by the way, it's very interesting to me. I know there's people from operations research here in the room. This is the problems that we're solving under the hood here are integer and mixed integer programs, which in principle are very complicated problems. They're NP-hard problems. In general, they belong to that label, that general class of computational problems. And it's true that the worst case problem in that class, in this kind of problems, can be very bad, but at typical instances, we can solve them very quick. So there's a lot of structure in this problem that can be exploited, which I think is interesting to people like you in operations research. Why? What is happening there? So the punchline is, with cardinality matching, use this function. Is the one that scales better to large data. So now we're going to have the treatment indicator like before. We're going to have our vector of moment covariates, but now we're going to specify this object here, which are called the targets. Okay, I'm going to balance the groups not only relative to each other, but relative to a target. And what is going to be that target? It's going to be the means of the covariates in the treatment, so that we estimate the average treatment effect on the treated while subsetting some of the treated units, while dropping some of the treated units, because we couldn't match them all together. Okay? So let me run this bit. Okay. So we want to find match samples that are centered around this covariate profile, as we call it. This covariate profile is this summary of statistics that describes a target population in principle, a target sample, and in principle, it can also be a target individual. So here I could have a vector of attributes that resembles you, for example, your age, your gender, and so on and so forth. Okay, and I find the largest match samples around you. That's the idea. Okay, the solver options are the same. And here we solve cardinality. We found the matches very quickly. Let's see how many match pairs we obtained. 99 now, a bit less. And we're going to check balance. And we can see that the treatment and match control groups are quite similar to each other, as measured, for example, by the standardized difference in means, but they're not only similar to each other, they're similar to the target, to the initial target, which is a way of increasing the external validity of the study, right? So that it's more generalized. Yes?
Use the naive question, but it seems to me that each configuration you make establishes certain hypotheses about the outcome. Could you explain this result in English? That is, what is the answer to the causal hypotheses expressed by this computation?
Okay, it's a really good question. The causal question that we're aiming to answer here is, what is the average treatment effect on the treated under the assumption of no unmeasured confounder? So we are adjusting for observed confounders by matching, and we are kind of anchoring the study around the target population of the treated subjects by making the means of the groups be very similar to the means of the treated population as we understand it from the original treated. Okay, so that's what we're doing. You also mentioned that here you're implicitly assuming stuff about the outcome model. That's true. Here we're only adjusting for the means of the covariates as opposed to the joint distribution of the covariates. This form of adjustment is fine if in truth the outcome model is linear. But if the model were to be something more complex, for example, with interactions between covariates, then I would need to balance more. So we're implicitly making that assumption. After matching like this, we can just take the difference in means between the outcomes, if we're assuming that underlying form of model. But we can also, after matching, use other methods, like, for example, regression or machine learning methods, so that the matching step kind of like puts less stress on the modeling step so that extrapolation is more limited. So I'm trying to acknowledge your question. Yes, there are assumptions about the model, and I'm trying to say how matching can help in taking care of that model that we're ultimately assuming.
So each matching has a different probability of a causal result being true.
I guess that in general that's right, but I think the same thing would apply to other forms of adjustment.
So you're exploring a wide range of models and try to determine the impact of treatment on the group.
I would say that this analysis is going to be valid under a certain class of outcome models, but we are doing it once. Just like in an experiment, we have one experiment. We don't have many experiments here. We're trying to build the best possible emulation of that experiment from the observational.
Thank you.
Well, yes.
Would there be a concern here on perhaps you're like close to the target where the target is the total population, but since you're removing some data points, perhaps you're not generalizing well to under subpopulations that you have in the data?
Okay, that's a good question. So here we're targeting one population, and that population may be different from, I don't know, the vulnerable population. Yeah, that's true. They are different target parameters ultimately. So in general, we can think that we are estimating not an average treatment effect, but a target average treatment effect for a given target population, and there can be different of them. And if in truth, the effect of treatment is modified by covariates, which is likely the case, we can imagine that the effects vary across populations. So yes, there is a trade-off. It's just a different question that we're asking to the data. To me, a very interesting line of research is, okay, I have my data set. I want to learn about many populations, but the question is really how to meaningfully integrate it in a way that we have valid inference. But procedurally, nothing stops you from doing it. Now I can go back and define another target match another target and match another target and match, and you can see how the point estimates vary all over. I think the question is then how to count for uncertainty in a proper way. Other questions? All right. So what we have just done is to find the largest cardinality match, the largest match sample of pairs that is balanced relative to that target. In this first matching step, we didn't emphasize how the individual units are matched. We just wanted balance in aggregate. But there are reasons in addition to looking for balance in aggregate, finding that the component pairs are as similar as possible in terms of observed covariance. So for example, in the context of randomized experiments, if one in truth were to have a study that was done in terms of matched pairs of subjects that were paired in terms of covariance that were predictive of the outcomes, that's how in truth the experiment was made. But then you get your data set and you forget about the pairing, you would be leaving money on top of the table. Okay, your standard errors around your point estimates that take into account that pairing structure would be lower. Similarly, in matching, something like that happens. And under certain models for sensitivity analysis, that pairing, if it's done in a way that it's predictive of the outcome, it can also reduce sensitivity to unmeasured. So that's why here we're going to add a step 2, where after matching the units, we're going to rematch them to emphasize closeness on a pair-to-pair basis. Aggregate balance is going to be preserved because the mean here is the same as the mean here, you know. They're the same units, so the mean is the same, but the individual distances between the units is going to be different, and that is going to matter. So step 1 was cardinality matching. Step 2 is going to be optimal matching in terms of distance. But not any distance, it's going to be a distance using a covariate, a pre-treatment variable that is very predictive of the outcome. The outcome here were the earnings in year 78. We're going to use the earnings in year 74 because it's a very strong predictor of the earnings. So we're going to solve this matching problem here, this match or distance matching, which is a way of doing optimal match. So we're going to run this basically following the same structure as before. We found the optimal matches very quickly. And now we're going to check balance. And we see that balance is the same table as before because the components units are the same. And when I compute the means, no matter how I sort them, the means are going to be the same. So that's the same. But we know that covariate distances are reduced. So here I'm going to compute the covariate distances in step 1 and step 2. And we can see that they are greatly reduced, right? So the covariate distances in step 1 were these. Now they are much smaller. We can see that the mean differences in outcomes in the cardinality matching step, which is the first row here, and the distance matching step are the same. We see an average treatment effect of $1,700, but their standard deviation is reduced. Okay? So here we see this thing about precision that we were talking. Because we're working on the matched pairs, as opposed to the differences on the groups in aggregate. So note that this is the first time that I look at outcomes. In all this discussion about matching, we haven't touched the outcomes until now when we have analyzed. that is a very valuable feature for some people because just like in an experiment, we can play a lot with the data, but in a way that it's objective. We're not using a design that produces the answer that okay, we can still do it here, but what I'm trying to say is that the steps are more clearly separated, the one of adjustment from the one of analysis, okay? Here, I showed you this in order to show how the distances matter in the rematching step. And what we can do next is to analyze the outcome. But we're going to analyze the outcomes doing that sensitivity analysis to hidden bias. So in order to explain what we're going to do here, we're going to go back to the slides, and I'm going to explain the model for sensitivity analysis. So design match basically implements this framework here that you're seeing. Okay. A new function that we have included recently in the design match package for R is what we call profile matching, which is quite similar to cardinality matching, but it takes this idea of balancing in aggregate kind of to the extreme, okay? The idea is that instead of matching groups jointly, we're going to balance each treatment group separately, one at a time, each of them relative to a summary of a target population that we care about. So in this sketch here, we have a target population on the top, which is characterized by those three covariates, female, green, and age. This is our observational data set. We have 3 treatment arms, A, B, and C. So far, we have had 2 only. And what profile matching is going to do is to find the largest unweighted or self-weighted sample that is balanced relative to that description of the data that I had initially. Okay. The reason we want to find this unweighted sample is so that the structure of the data is very kind of clean. There are no differential weights, but we can easily relax that requirement via weighting. What it's appealing to me about this way of adjustment is that the structure of the data, it's unweighted, which is handy, for example, if after the adjustments you want to use methods that do not readily admit differential weights. So some machine learning procedures, they don't readily off the shelf admit differential weights. Also, if you want to plot the outcomes, you know, it's very handy because the structure of the adjustments of the adjusted sample is just a sample without any weights whatsoever. And the other reason is that since we're matching to the profile, in principle, we don't need access to the individual level data of the target population, which may be unavailable due to confidentiality reasons. For example, if you're working with CMS data from Medicare, it's likely that we will not have access to the population of all Medicare recipients, but the Centers for Medicare and Medicaid Studies may be willing to share with us descriptions of those populations. Then we can still do that because we're matching each sample towards that summary. And this is interesting to me because once we see that we're doing this, that we're matching to a description, we can see that that description can be the description of a single individual. So that we find samples that are balanced around you or me. You know, it's kind of like samples that kind of like have us in their center. So we go to medical records, a patient is going to undergo a given treatment. I want to find all the largest sample of patients like me which have encountered a similar treatment. It's a way of making these queries in the data. Mm-hmm. And the other feature is that since we broke the matching problem into treatment groups, we can easily, from a procedural standpoint, not a data standpoint necessarily, accommodate many treatment groups. So we could have 10 treatment arms, for example. We're matching one arm at a time, which is something that can be complicated, for example, if we're estimating a multinomial propensity score. With many treatment categories, it can be quite difficult. Then the matching step, when you have many treatment groups, optimal matching with just 3 treatment groups is a very hard problem. What to say 10. So breaking the problem also helps in that way. And in the code here, okay, it must be another version. I have an example of profile match so that you can run it too. Okay, so this is what we call profile matching for personalization. The idea is that the match samples are built around a single person. Now what I wish to do is to connect matching to other forms of adjustment, in particular to weighting. Remember that our estimand was the average treatment effect, and under the unconfoundedness assumption, we represented that target estimand as something that suggested this regression strategy, where we impute the missing potential outcomes by fitting a model. We can also represent that estimand using weighting, inverse probability weighting. And then the question is how we estimate those weights. By modeling the propensity score or by directly balancing the covariates. In connection to matching, one can say that there's a connection between the two, where matching is a form of weighting units, where we're explicitly matching or assigning units in the treatment group to the control group. From a data standpoint, a difference between the two approaches is how the weights look like in the data set. In cardinality matching, I have emphasized a lot this idea of having weights that are 0 or 1, so that the data set is very clean. But that comes at a cost, as I said before, in terms of efficiency. If I can use portions of us, I can get to use more information in an intuitive sense. So if we were to relax that integrality 0-1 constraint in matching, I could be using more information. That is what weighting is basically doing. So to contrast the methods, I think that it's fair to say that matching is emphasizing study design and interpretability in terms of replicating the structure of this randomized experiment in the observational data in a way that is very clear. So I show you the sketch with the treated and the controlled data sets and the arrows, that's what is going on with matching. It's very clean what is happening. In weighting, we lose a bit of that because now the units are stretched and shrunk in a way, which is not terrible, but we're losing the thing about keeping the unit of analysis intact. But weighting, on the other hand, emphasizes statistical efficiency and computational tractability, because typically the weighting problems that we solve are in the polynomial, okay? So in principle, they're a lot more tractable. I say the word in principle because in my experience, I've been quite surprised to see what Gurovi and other solvers can do in the matching problem. So I think it's definitely the case that weighting is faster, but still, we shouldn't shy away from matching from that reason, because we can solve very large instances of it. And these two approaches, matching and weighting, they're both what can be thought as part of the design of the study, no outcomes, and they're both modular in the sense that we can use them with other regression approaches to form W robustness. So one form of weighting is what we call balancing weights, where we're minimizing a measure of dispersion of the weights subject to balancing constraints, where now the balancing constraints are not the covariates X, but they're transformations of the covariates X. We use the word B here, coming back to your question, to refer to basis functions that span a function for the outcome mode, that it's unknown. But we want these B functions to be as expressive as possible so that we can adjust against a very general unknown function. Importantly, with weights that are non-negative, I would say, so that if we get the function model class wrong, then we're not that wrong, as if we were extrapolating a lot. So this form of weighting has a very strong connection to the matching problem, where basically, instead of maximizing the size of the study, we're maximizing the information of the study relative to an estimator as defined by the weights, subject to more expressive covariate balance. And I wish to comment on machine learning here. So I motivated matching by, in the context of this toy example, saying that by hitting the line, when there's limited overlap in covariate distributions, we can get it very wrong. But of course, one can estimate a more flexible machine learning mode. So this example is from Jennifer Hill from NYU. And what she suggested do it here was using flexible Bayesian non-parametric models, BART in particular, to learn these response surfaces as flexibly as possible, to then do the imputation, but with a more flexible mode. So here, machine learning can help a lot. And machine learning can also help a lot in modeling the propensity score. So you can flexibly estimate the treatment model and the outcome model and put the two things together in a double robust estimator, so that along the lines of efficiency, you get an estimator that converges to the truth at a very fast rate, in spite the component models are estimated at slow rate. That is, I think, the main thing about double robust estimate is that you can estimate each of the components very slowly, very flexibly, but when you put them together, you get fast rate. So here, machine learning can help a great deal. What I'm emphasizing today is methods that kind of emphasize more of this transparency and this connection to randomized experiments. And I think that the approaches are complementary. Okay, so for example, here you can use balancing weights and then machine learning to estimate the effects. The same thing with matching. But one of the reasons we're doing matching is because at the end of the day, in an observational study, there's the question about hidden bias. Okay, so we adjusted for these 10 covariates in the data set, but you missed ability, you missed motivation, you missed other traits of the worker, which is really what is driving the error, not the observed covariate. So we want to have a statement that says how sensitive, how robust are our results to the influence of such hidden confound. And one could argue that matching facilitates a transparent and simple model for sensitivity analysis. And that's what I'm going to explain next. So the point is that we did matching to transparently adjust for observed or overt biases, and now so that we can make statements about hidden bias. That is the idea. The question is, sure, association is not causation, but can we say something more than that? In other words, can we quantify the magnitude of hidden bias due to an observed confounder that would have to be present to explain away my statistically significant effect estimate. Remember, in our last cardinality match, we find a point estimate of like $1,700, right? Which is statistically significant. Just based on that analysis, predicated on this assumption, we would say there's a significant effect of labor training to that extent. The question is how much hidden bias has to be present to wash away that conclusion, to make that statistically significant finding insignificant. In other words, how much do we have to depart from this assumption in order for that result to go away? That's what a sensitivity analysis is. The intuition is that weak associations can be explained away by very small biases, but only very large bias can explain a strong association. All this in large studies. And our model is going to go as follows. Each unit J is going to have a probability of receiving treatment. And we're going to say that a study is free of hidden bias if this probability pi j of getting the treatment is free of observed covariates only, as opposed to the unobserved covariate U. So we're saying that. So we're saying that here that pi j, it's a function lambda, if you wish, of xj, but only the x's. Okay, there's no rule for the u's here. Okay, so we're going to say that a study is free of hidden bias if this is what is happening. And we're going to say conversely that there's hidden bias if two units with the same observed covariates x have different pi's. And the question that a sensitivity analysis asks is, how would inferences about treatment effects be altered by hidden biases of various magnitudes? In other words, the question is, how large would need to be the influence of that hidden covariate U to alter the qualitative conclusions of the study? The qualitative conclusions where the labor training program mattered, and now we're saying it doesn't matter, it doesn't research. So for this, we're going to use matching. We're going to match on the observed covariate x's. So we're going to have two units, I and j, which are matched in their x's, but they possibly differ in their pi's, in their probabilities of receiving treatment, because of the unobserved covariate. And we do this by matching. And then what we're going to do is to compare the odds of receiving treatment of unit J to the ones of receiving treatment of unit K. Again, these are two units that are matched on their X. The question is how much these odds can differ before our statistically significant results cease to be significant. And what the model says is that these odds ratios, which is the ratio of these odds, so it's a division of divisions, differ at most by a factor gamma. In a randomized experiment, gamma is equals to 1. The question is, how large can we make gamma and these bounds be more different to each other before our statistically significant results cease to be significant? So what we're going to do is, after matching, increase gamma and compute the p-values for different values of gamma, keeping track of the maximum value of gamma where we still get a statistically significant, okay? And when we cross that border, okay? So for these two gammas, one can show that the worst case p-value. And the question is how far we can go before that worst case p-value ceases to be statistically significant. That is what the sensitivity analysis. This is what the model says. which, by the way, this model is implicitly saying that the unobserved covariate affects linearly the logs of receiving treatment. So there's a functional assumption there. So that's what the model is. So if gamma is equals to 1, the study is free of hidden bias. For gamma greater than 1, there is hidden bias. And the question is how far we can go. Gamma is a measure of the degree of departure from a study that is free of hidden bias. How much we can depart from a study that is free of hidden bias. And for this, what we're going to do is to go back to our labor training example. And these are the outcomes that we're comparing. So these are the match pair differences in earnings. We basically have a point estimate of 1,700 here, which if we test it using the Wilcoxon sign rank test statistic, we have a point estimate of like 1,800 and a p-value of 0.02, so it's statistically significant. The question is, how much can we increase gamma before it ceases to be significant? Here we have the differences in match pair outcomes. And here we see the p-value that we have, basically 0.02. And as we increase gamma from 1 to 1.01, we can see that now the best and worst case p-values start to differ. You know, it becomes larger and larger and larger. And so we're admitting more discrepancies in the probabilities of receiving treatment due to the unobserved variable u. The question is how large gamma can go before this p-value is greater than 0.05. And so we go until here. Okay. So the bias that this match study tolerates is a bias of basically 1.1. So this is saying that two match units that were matched based on those 10 observed covariates can differ in their odds of receiving treatment due to an unobserved covariate, such as ability, by a factor of 1.1. So it's not a very robust result, the one that we obtained. But the point is that we're adding this layer to our typical p-value, which speaks about the robustness of that p-value to a hidden confounding. Some studies are going to be more robust than others, but here we are kind of like adding some evidence to how strong is that causal claim. How sensitive are our results to violations in this case? Yeah, and we did matching with that in mind. So here are the results summarized. And I have to acknowledge that there are many models for sensitivity analysis. Here I'm following Rosenbaum's model for sensitivity analysis for match groups. But there are other approaches, like the ones by Robbins, by Vanderbilt, and Pong-Ding and others. And here are two functions to do sensitivity analysis after match. All this analysis is predicated on the sharp null hypothesis of no treatment effect, the one that I said that there's no effect on anyone, but it can also be relaxed to the Niemann's weak null hypothesis. Okay, now we have been talking about experiments, observational studies, overt and hidden biases, and how we can use matching to find that randomized experiment that is hidden inside the observation in a way that is optimal and in a way that we can do sensitivity analysis to hidden bias. Now I want to talk a bit about other methods for adjustment. We talked a bit about weighting. I want to talk also about regression. I want to come back to the question of how is regression acting on the data to emulate certain features of a randomized experiment. So far, we have had a treatment and a control group, and we have been worried about contrasting the outcomes in these two groups, but we haven't talked much about the target population, except for that discussion on cardinality matching and profile matching. And the point is that in general, in addition to randomization, these samples are going to be a random sample from a population. These samples here have a similar structure to the population, so that our inferences readily extend to such population. Right? So in this setting, some key features of randomized experiments are covariate balance, study representativeness, self-weighted sampling, and sample boundedness. What does that mean? In this setting, because of randomization, we have balance that we know. Because we randomly partition a random sample from the population, each of these samples is representative of the population. And without any weighting whatsoever, we have a similar structure as the target population. And the estimators are sample bounded in the sense that their point estimate, because of balance, they lie in the convex hull of the observer, as opposed to extrapolating. The question is, how are these features preserved or not with other methods for adjustment? In this tutorial, we have emphasized a lot that experimental ideal. The question is, in terms of that experimental ideal, what is happening with other methods, specifically with regression, in terms of these four attributes? In particular, when we move to the world of observation. So in observational studies, how is regression emulating those features? So the question is, where's the experiment when we do linear regression adjustments in observational data? And compared to some extent, matching regression and weighting in terms of those four attributes. The question is, how are these methods acting on the individual unit level data at hand without resorting to asymptotic approximations, using closed form expressions and seeing what are the math programs that are solved by these different procedures, emulating a randomized experiment. So the procedure is this linear regression model where we have the observed outcome regressed on a vector of observed covariates and this treatment indicator, and we're interested in estimating this coefficient tau for the average treatment effect, okay? The point is that estimating this coefficient tau via OLS, ordinary least squares, is equivalent to this imputation estimator that I was describing before, which in turn can be written as a weighted estimator like this. And in the case of regression, one can obtain closed form expressions for this weight and see how the weights are acting on the data in terms of balance, representativeness, and so on. Yeah, so in this paper here with Ambarish Chattopadhyay, what we did was to obtain the expressions of these weights to see what is regression doing in terms of balance and so on. If the observational study looks like this, there are two forms of regression, one can say. This one here, where we fit a general regression model on the overall treatment and control samples, and one where we fit separate models on the treatment and control samples, or equivalently, fit a longer model with interactions. The point is that this procedure here, which is perhaps the standard use of regression, or the first use of regression for causal inference, it's doing something like this, where you have exact mean balance in the covariates, but not necessarily towards the target population. So the means are perfectly balanced, but not around the target population. It can be another population. It's not what one can characterize as the natural population of treated or controlled subjects or the overall population of subjects, with weights of minimum variance, which is great, but that can be negative, okay? Which is questionable. Conversely, that other approach of regression, which is fitting these separate models, now you get it right for the overall population. The weights have minimum variance and the weights can still be negative. If one were to use inverse probability weighting by fitting, for example, a logistic regression model to obtain the weights, the structure of the data set would be something like this. It is possible that a few observations have a very large influence on the final point estimates. But by using these other approaches that I was referring to about balancing weights, one can more explicitly restrain the variability of the weights and covariate balance to target more directly. So we see that these guys here have less of an influence. To compare the methods in some way, with matching, we're doing something like this. With regression, we can balance very well, but we're relying very heavily on the model to the extent that the weighting doesn't make a great deal of sense with negative weights. And if the model is misspecified, this can have consequences. And with weighting, we have a differential weighting, but with keeping the unit level weights non-negative. So this is a way of saying what the different approaches are emphasizing. I would argue that matching is emphasizing study interpretability and design. That is what is happening with the data set. Regression is emphasizing a lot efficiency, but based on a specification of the model. It's kind of like, as Hiro Inban says, linear regression is taking linearity very seriously. And if the model is wrong, then your point estimates can be quite wrong. And weighting is an adjustment that it tries to maximize efficiency. But I would argue that in a way that it's more robust than traditional use of linear regression. For these different approaches, we have written different R packages. So far, we have been discussing the design match package for R, but we also have R packages for doing weighting in the SVW package for R and the LMW package with Ambarish Chattopadhyay and Noah Greifer. It's work that we did when Ambarish was here as a student. Noah is here at the IQSS. And you can download them from the internet easily. So that's how we can compare these different methods for adjustment. Okay, so far, are there questions so far? No? Okay, so everything we have done so far, it's to emulate, to approximate this experimental ideal based on an assumption that says there are no unmeasured confounding. But the point that I want to make is that if this is a strategy that aims to control for observed variation in an explicit way, there are these other approaches which aim to control for an observed variation by relying on these devices which are called instrumental variables or discontinuity. What is the idea? What is an instrumental variable? An instrumental variable is kind of like this magical variable, as Miguel Hernan and Jamie Robbins say, which is a variable that if in truth behaves as we assume it does, we don't in principle need to adjust for all the confound. An instrumental variable Z is a variable that affects the outcome only through the treatment, in such a way that the treatment can be confounded by an unobserved covariate U, but it doesn't matter. Because if we make smart use of this variable set in a certain form of estimator, we get it right. So an instrument is a haphazard push to receive treatment, which affects the outcome only through the treatment. And this is one of the signature methods in economics and the social. You can use also matching in these settings, weighting in these settings, and so on. The target experiment that we're trying to approximate here is what can be called an encouragement design, in which subjects are randomly assigned to receive treatment. Another thing is whether they actually take the treatment. So you're encouraged to take the pill, but that doesn't guarantee that you'll take the pill. That is the kind of experiment that we're approximating. And then another opportunity to estimate causal effects are discontinuity designs, in which treatment assignment is governed by some rule, such that for values smaller, say, than a certain cutoff, subjects are assigned to treatment, and for values greater, they're assigned to control. So the idea is that by restricting the analysis to a neighborhood of this cutoff, okay, in essence, you have a randomized experiment. Around that cutoff, treatment is as if random. That's basically the intuition. Which is another strategy that is often used to estimate a causal effect. All right, to wrap up, in this tutorial, we have studied some principles for causal inferences, focusing on study design, specifying the target population in very clear ways, and stating the assumptions under which these analyses are indeed causal, so that we avoid stronger parametric specifications and that we characterize the sensitivity or robustness of our results to hidden bias. Trying to emphasize what it's a transparent study design, in which we know how we're acting on the data, whether we're extrapolating or not, whether we're dropping observations or not. And one can argue that matching adheres to these principles in specific ways, but again, there's no free lunch. Matching is strong in terms of transparency, but in terms of efficiency, there are other methods which are better. So I was supposed to finish at 11:50. I think that we're on time. Thank you so much.